Hey everybody, Sukanya here. Today we're going to be taking a look at two properties of vectors. The first is collinearity, and then we're going to be taking a look at coplanar. So let's take a look at what does collinear mean. So let's assume that we have two vectors, A and B, and remember, whenever we're dealing with vectors, it involves the x, y, and z axis, so the three-dimensional axis. So vectors A and B are collinear if this is true, where x and y are not both 0. So x and y are just scalars, but honestly, I think this is a little bit tricky to wrap your head around. It is the formal definition, but there is a better definition that I think is much more easier. So while this is true, I'm going to go to the next definition where vectors A and B are collinear when vector A is equal to a scalar multiplied by vector B, or vector B is equal to a scalar multiplied by vector A. Essentially, if you want to think about it geometrically, there are two ways vectors can be collinear. The first is that they are parallel to each other. So if I say vector A and B are collinear, it means that they're parallel to each other. The second way that you could think about it is that if A and B are collinear, then that means they must fall on the same line. And I think this is what most people think about when they hear the term collinear, because it's linear meaning line, meaning that they fall on the same line. Now let's actually see if two vectors are collinear. How are we going to prove that? So we have our problem right here, and it says show that this vector here, I'm going to say that's vector A, so that is 2i minus 4j plus 5k. You might also see vectors possibly written in this form, 2, negative 4, 5. In that form, it's the same exact way. And this other vector, I'm going to say that's b, negative 4i plus 8j minus 10k are collinear. Now, what I want to do is I am going to use this or this method. So looking right off the bat, I see that vector b is equal to negative 2 times vector a. And the reason for this is because if I do 2 times negative 2, I get negative 4. If I do negative 4 times negative 2, I get 8. And if I do 5 times negative 2, I get negative 10. So vector b, this vector over here, is equal to negative 2 times the vector a. And from here, we know lambda is equal to negative 2 because this is in the form of this one right over here. And since they're both in that same form, we can definitely say that vector a and vector b are collinear. Now, you might think that is it for collinearity, but there's actually a second part. So one important thing to note over here is that this is talking about vectors. We're seeing if vectors are collinear. But what about points? What if we want to find out if 3 points are collinear? How are we going to do that? So our next theorem is going to be points A, B, and C are collinear if, and that is supposed to be an A, if A is equal to lambda B or B is equal to lambda A. So it's basically the same exact thing. Now you might be thinking, how did we get from points here to vectors A and B? Well, I want to clarify a few things first. That you might have noticed that instead of having 2 vectors, as we did earlier, we have 3 points, which brings up an important distinction that if you're trying to find if 2 points are collinear, just 2 points are collinear, that's kind of not a real question, because if you see over here, any 2 points are going to fall on the same line, no matter how you draw them. So it's kind of pointless to say that prove if 2 points are collinear. What we want to prove is that if 3 points are collinear, because, for example, these 3 points, they are not collinear, but these 3 points over here, they are collinear. So we want to see if these 3 points are collinear, right? Now, I'm going to read the question, show that P 1, 2, 3, comma Q 3, 5, 7, and then R 7, 11, 15 are collinear. Now I'm just going to roughly draw this. I'm going to say this is P, this is Q, and this is, this is R. So I'm going to prove that they all fall on a straight line in this case. And over here, it means whenever we're talking about points, it does mean it falls on a straight line. When we're talking about vectors, then it could either mean they're parallel or they fall on a straight line. But for points, it's that they must fall on that straight line. So we have P, Q, and R. And another way that we could show that these are collinear is that if I prove vector PQ is collinear to vector QR, and this is looking a lot like this case over here. If I can prove vector PQ is collinear to vector QR, then I have proven PQR are collinear. It's basically the same exact method we looked at earlier, but this time we have to go from points to the vectors over here. So how are we going to find PQ? So we have PQ right over here, Q minus P. So I'm going to do 3 minus 2, which is, or 3 minus 1, which is 2. 5 minus 2, which is 3. 7 minus 3, which is 4. And then this is vector. We can do it like this notation as well. And then what do we have? We have QR. QR. So we do R minus Q. And now we have to prove if these are collinear. And right off the bat, I see that QR is equal to 2 times PQ, because if you multiply 2 times 2, you get 4, multiply 3 times 2, you get 6, multiply 4 times 2, you get 8. So in this case, our lambda is 2, and these points are indeed collinear. So that was essentially all for collinearity. There are 2 subparts, one for vectors and one for points, so just keep that in mind what the question is asking you to prove, vectors or points. Alright, so now let's move on to coplanar. So let A, B, and C be 3 given vectors. Then all 3 vectors are coplanar if one vector is the linear combination of the other 2. And what does linear combination mean? Well, this is the definition right over here. So you have one vector, C, is equal to x times vector A plus y times vector B, where x and y are both not 0. So linear combination basically means that you're multiplying a scalar by a vector, and then just adding those 2, like over here. You guys see that? Now, let's look at it graphically. So on the left side, this is an example of a non-coplanar. So this is supposed to be A, and then let's say B, and let's say C. The reason I put X, Y, and Z is because let's assume that vector A is the x-axis, vector B is the y-axis, and vector C is the z-axis. You guys can see that they do not share a common plane, right? I mean, there's the xy plane, that's different from the yz plane. Like none of these vectors lie on the same exact surface, as I like to think about it. They're all lying in different surfaces. Now, this right over here is coplanar because they're all lying on the same surface. There's not any vector protruding out. It is just all on the same level. So A, B, and C in this case are coplanar. Now let's actually take a look at an example. So in this example, we're going to be dealing with points. So essentially the exact same thing is going to be the same with vectors. It's just that with points, it's a little harder since we need to convert points to vectors first. So it's saying prove points A, B, and C are coplanar. Okay, so essentially we're trying to prove that points A, B, C, and D, they all lie in the same plane. It's a bit difficult to visualize, but just visualize that they're all on the same surface, right? So then let's say this is the z-axis. I don't know, maybe this is the y-axis and this is the x-axis. So we're all trying to say that A, B, and C, D, they all have to be on the same plane. What I'm going to do the same exact way that I did the previous problem. I'm going to find the vector. So I'm going to say vector AB, vector BC maybe, and then vector CD. Those vectors should be coplanar. And the reason I'm only doing 3 is because it will be satisfied with only 3 vectors, because as we saw over here, we just need these 3 vectors, right? So I am going to say that AB, I'm going to find AB first. That is B minus A. So that is, I'm going to have those brackets now because I'm making this into a vector. 1, 2, 2. BC is going to be C minus B, so that is going to be 1, 3, 3. And then CD is going to be D minus C, so D minus C, which is 2, 4, 4. Now I have to apply that above formula, which said something like C is equal to XA plus YB, where x and y cannot be equal to 0. So that is one thing to note. I'm going to take this as c, this as a, and this as b. So we can just substitute those in. So I'm going to write it in a different form. I'm going to say 1i plus 2j hat plus 2k hat. I'm just converting these angular bracket into their components is equal to, and now I'm going to have x as my constant. A we said was this right over here, so that is 1i hat plus 3j hat plus 3k hat. And now I'm going to work with this plus y. B is going to be this right over here, so 2i hat, let me move it that way, 2i hat plus 4j hat plus 4k hat. There we go. Now I'm going to simplify this. So I've simplified the right side all the way, and this is what I got. Now what I'm going to do, I'm going to group the i's together. And the reason I'm going to group the i's together, the j's together, and the k's together is so that I can set the coefficients equal to the left and the right. So I am going to take out the I out of the underlined term, so x plus 2y I. I'm going to take out the j, so 3x plus 4y j, that is from these two terms. And then lastly, I'm going to take out that k, 3x plus 4y k. 3x plus 4y k. And I'm going to rewrite this side. I'm just going to have I plus 2j plus 2k. Now, in this case, I am going to set these coefficients equal to each other. So x plus 2y is going to be equal to 1. 3x plus 4y should be equal to 2. 3x plus 4y is equal to 2. I'm going to scroll down a little bit here. 3x plus 4y is equal to 2. And then 3x plus 4y is also equal to 2 right over here. So in this very rare scenario, we actually have these two equaling 2 right over here. So now I know that this is equal to 2. I'm going to label these 1, 2, and 3. And we're just going to solve system of equations. So I'm actually going to take these two equations and I'm going to solve for x and y. So from this, I got x is equal to 0 and y is equal to 1/2. And that is perfectly valid, right? Because our condition says that these 4 points are collinear as long as the scalars are not both equal to 0. I should actually mention that. Not both 0. And over here, just our x value is 0, so that is perfectly fine. So we can for sure conclude that points A, B, C, and D are coplanar indeed. And that was a little crash course onto collinear and coplanar.